Dear students, today we are going to see the performance of the experiment to determine particle size and particle size distribution using microscopic method. So the apparatus what we will require for this experiment is you are going to need a microscope, eyepiece micrometer scale, stage micrometer scale, glass slide, cover slip, etc. And in chemicals we will require any powder sample or diluted suspension. So the term micromeritics, okay, it is nothing but it is the science or it is the study of the technology or study of small particles. Okay, so the term micromeritics is the science and technology of small particles. It basically deals with studying these small particles. So the powder properties, okay, whenever you are dealing with any powder, okay, it has got some properties which are very important or which will determine the overall formulation or the stability of your formulation. Okay, so the powder properties are divided into two categories. The one is called as fundamental properties. Okay, it is nothing but it includes the particle size and shape. Okay, and the second part or the second type of property is called as the derived property. It is derived from the fundamental ones. It includes derived property include bulk volume, granule volume, tap volume, true volume, bulk density, granule density, true density, flow rate, angle of repose, porosity, bulkiness, compactness, consolidation, and compression. So it is this the study of fundamental and derived properties of individual as well as a collection of the particles. So the size and the surface area, okay, size is going to determine your surface area. Okay, so the size and the surface area of the particle, it can be related to the physical, chemical and pharmacologic properties of the drugs. Clinically, the particle size of a drug, it can affect its release from the dosage form that are administered orally, parenterally, rectally and topically. So the particle size of the drug is very important. Why? Because it affects the release from the dosage form. So the successful formulation of suspensions, emulsions, tablets, along with its physical stability and pharmacological responses, they altogether depend on the particle size of the product. So what are the applications of particle size? First, it is going to govern the release and dissolution. Particle size and surface area, it influences the release of the drug from a dosage form that is administered orally, rectally, parenterally and topically. Higher surface area brings about intimate contact of the drug with the dissolution fluids in vivo, and if smaller is the particle size, more will be the surface area and more will be the rate of dissolution. Okay, so if smaller is the particle size or higher is the surface area, it will definitely increase the drug solubility and its dissolution. The second application is absorption and drug action. The particle size and the surface area, it influences the drug absorption and subsequently the therapeutic action. The higher is the dissolution, the faster is the absorption, and hence quicker and greater will be the drug absorption. Next application is physical stability. Micromeritic properties of the particle, that is the particle size in the formulation, it definitely influences the physical stability of the suspensions and the emulsions. The smaller is the size of the particle, the better will be the physical stability of the dosage form owing to the Brownian motion of the particles in the dispersion. The next application is dose uniformity. Good flow properties of granules and powders are important in the manufacturing of tablets and capsules. The distribution of particles, it has to be uniform in terms of number and weight. Very small particle size causes attraction, which in turn destabilizes the suspension by coagulating. Now we will see in detail about particle size and particle size distribution. Particle size represents the dimensions of the solid powders, liquid particles and gas bubbles. Particle size mainly influence the rate of dissolution, and ultimately it is going to affect the rate of absorption. So absorption rate of poorly soluble drug, it can be improved by reducing the particle size and thus enhancing the bioavailability of the drugs. Particle size is also considered during development of new chemical entities, that is NCEs, as it affect physical properties of the active pharmaceutical ingredients and excipients. Particle size and shape, they significantly affect various manufacturing steps like mixing, granulation, drying, milling, blending, coating, encapsulation and compression. As per ICH guidelines, particle size is critical parameter which is going to affect the safety, efficacy and more importantly the stability of solid dosage form and certain liquid dosage forms like suspensions and emulsions. So during manufacturing of solid dosage forms like tablet and capsules, particle size, it influences a large number of parameters in processing, including capsule filling, porosity and flowability. Similarly, in suspension, physical properties and particle size of dispersed particles both affect the stability of the formulation. Now let us see about particle size distribution. Any collection of particles is usually polydisperse. That means what? That polydisperse mixture, it has got particles of different particle size. When the powder collection, it has got particles of same size, then it is called as monodisperse. But whenever we have any powder sample, it is never monodisperse in nature. It is always polydisperse. That is, it is a mixture of powders with different particle sizes. So it is therefore necessary to know not only the size of certain particle but also how many particles of different size exist in that sample. Thus we need an estimate of the size range present and the number of weight fraction of each particle size. This is the particle size distribution from which average particle size for the sample can be calculated. Particle size is related to the shape and surface area of individual particle. Particle size distribution has profound impact on the stability, aesthetic appearance, rate of absorption and bioavailability of the drugs, and is also basic need of various regulatory agencies to establish particle size distribution of excipients as well as pharmaceutical formulations. So there are many ways in which you can express the particle size and diameter. So the size of a sphere is readily expressed in terms of its diameter. The surface diameter, which is denoted as ds, is the diameter of a sphere having the same surface area as the particle. The volume diameter, denoted as dv, is the diameter of a sphere having the same volume as the particle. Projected diameter is dp, is the projected diameter of a sphere having the same observed area as the particle. The Stokes diameter, denoted as dst, is the diameter which describes an equivalent sphere undergoing sedimentation at the same rate as the asymmetric particle. So this is the list of all equivalent spherical diameters with their respective definitions and formulas. You can see here surface diameter, volume diameter, projected area, diameter, Stokes diameter, sieve diameter, volume surface diameter, maximum length diameter, hydrodynamic diameter, aerodynamic diameter. Okay, this is the definition of each diameter. By what method you can determine that particular diameter, and this is the formula for calculating that individual diameter. Now let us see the expression of particle in diameter for non-spherical particles. Okay, whenever you deal with powders, you seldom have spherical particles. Okay, the polydispersed powders or granules, they are not complete spherical in nature. They are very irregular in nature. Okay, So how you can determine the diameter for non-spherical particles, okay, that we are going to see now. So this figure, it represents the diameter for measurements. The first is the Martin's diameter. If you see this, it is the Martin's diameter. Okay. Now let us see how it is defined. It is the averaged chord length of a particle which equally divides the projected area. Okay. Then next is the ferret's diameter. It is the average distance. This is the ferret's diameter. It is the average distance between pairs of parallel tangents when you draw tangents at these points, okay, of the projected outline of the particle. The distance in between these two tangents is will give you the ferret's diameter, okay. And the last is the projected area diameter. It is the diameter of a sphere having the same projected area as the particle. That means what? You have to imagine a sphere, okay, which will cover this whole distance, and the diameter of that sphere will be the diameter of your irregular particle, okay. Now let us see what exactly is optical microscopy. It is a technique which is used for the process of counting the uh, size of the particles. So optical microscopy is usually used for the characterization of particles whose size is ranging in between 0.25 to 100 micrometers. Optical microscopy technique is applied for determination of particle size in suspension, aerosol and globule size of the emulsions. So in this method, the required sample size is less than 1 gram. The particle size in optical microscopy is expressed by the projected diameter, that is the diameter of a sphere having the same area as that of the irregular particles when observed under a microscope. So advanced microscopes, they have better resolving power and can measure size in nano range as well. Ultra microscopes, electron microscopes, scanning electron microscope, that is SEM, transmission electron microscope, TEM, they can also be used so that you have a very good resolving power for the measurement of the particle size. Now let us see what is the procedure. First, the eyepiece of the microscope is fitted with a micrometer. This eyepiece micrometer, it is calibrated using this stage micrometer. Okay, this is a stage micrometer. You have to calibrate the eyepiece with the stage micrometer. Then you will replace this stage with a glass slide on which you have put your powder or the suspension. Okay, so the powder sample, it is dispersed in a suitable vehicle in which it does not dissolve and its properties are not altered. Okay, you can disperse it in water or in paraffin oil. So this sample is then placed on a slide and it is placed on the stage under the objective of the microscope. Around 300 to 500 particles, they must be visualized and its diameter must be measured. So their diameter is noted and the mean is computed. Okay. So using this number of particles and the diameters, you can calculate different types of diameters of the particles, and which will ultimately give you the particle size distribution. Okay. Now we will proceed to perform this experiment.
Now we will see the performance of the experiment to determine particle size and particle size distribution by optical microscopy. Okay. The method which we are using here is optical microscopy. You call it, the method's name is optical microscopy, or you can also write the aim as to determine particle size and particle size distribution by microscopy method. Okay. So it signifies that we are going to use the optical microscopy method. Okay. So before starting the experiment, in the requirement we had seen that we require a stage micrometer and we require an eyepiece. Okay. So this is the stage micrometer. Okay. Now you have to keep in mind that this stage micrometer is used for calibration of this eyepiece. This is the eyepiece. Okay. If you just see it, on it engravings are given. Okay. So, so the stage micrometer is used for calibration of this eyepiece. Okay. And this eyepiece we are going to use for determining the particle size, to measuring the actual particle size. Okay. So now we will see how we are going to perform the calibration of eyepiece. Okay. So as you know that we are going to use stage micrometer. Okay, this stage micrometer is used for calibration. Now this stage micrometer, it has got a line, okay, a line of 1 mm is drawn on it, and this 1 mm line is divided into 100 divisions. Okay, so now as this 1 mm is divided into 100 divisions, one division on this micrometer stage, it becomes equal to 10 micrometers or 0.01 mm. Okay, then we have eyepiece. Now this eyepiece, it has engraved a 10 mm line, and this 10 mm line is divided into 100 divisions. Okay, so one division is equal to 0.1 mm. Okay, this is the thing. Okay, now what we do, first we will take the stage micrometer, we will place it on the stage of the microscope, and then we will place the eyepiece in the eyepiece cavity of the microscope. Okay, we will make the two lines of this eyepiece to coincide with the two lines of the stage micrometer. Okay, then we will calculate or we will measure how many lines falls in this two particular points, in this two particular coinciding lines. Okay, that value we are going to use. Okay, now suppose for example the x division of stage micrometer, it coincides with the white division of eyepiece, then the formula, okay, we are going to use is 1 division of eyepiece is equal to x into 10 divided by y. Okay, now the stage micrometer and eyepiece which we are going to use, we have already calibrated it, and we found that the 8th division of the stage micrometer, it coincided with the 6th division of the eyepiece. Okay, so for our eyepiece and stage micrometer, 1 division of eyepiece is equal to 8 into 10 divided by 6. It becomes to 13.3 micrometer. That means the distance between 0 line, okay, 0 point of eyepiece to 1 point of eyepiece is equal to 13.3 micrometers. Okay, so this is all about the calibration of eyepiece. Now we will proceed with the actual experiment. We will see the process of calibration once again. We have seen the calculations of calibration, but we will see the procedure. Okay, now this is the stage micrometer. We will place this stage micrometer on this stage of the microscope. Okay, then you will have to take out this eyepiece of the microscope, and we have replaced it with the eyepiece which we are going to use to measure the particle size. Okay, now you have to adjust it. Okay, so now it has been adjusted. Okay, now we will see how it is seen or visualized. Now this is the calibration. Okay, so if you see the you can clearly see the lines of the eyepiece as well as that of the stage micrometer. Okay, so now you from this you can say that the eighth line of the stage micrometer, it coincides with the sixth line of the eyepiece. Okay, and then you will go for calculation for the process of calibration. So when we are going to perform the experiment, at that time we are going to take a size range. Okay, the size range will be 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25, and 25 to 30. Okay, it is in micrometers. Okay, so we will write this range, and when we are going to actually measure the particle size, at that time what we are going to do, when we measure the particle in the size range of 0 to 5, suppose I have measured two such particles, so I will write in front of that range as 2 lines. Okay, just like we do it in stats. Okay, now for example, in 5 to 10 range I have taken 15, I have measured 15 particles, then I'll write 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5. Okay, that means there are 15 particles. Okay, this, why we are going to do this? This we are going to do during the actual measurement. You cannot count like in 0 to 5 there were two particles. You cannot remember this. Okay, because at the same time you will be recording the number of particles in all this size range. Okay, so to make it simplify, if you measure a particle size in this range as one particle, you will immediately write 1. If the next particle is in between this range, then immediately you write this. If the next is in this range, immediately here you are going to write this. Again, if the particle comes, next particle is in this range, you will just write a line. Okay, so this is the way we are going to measure the particles. Okay, now we will see how it is done. Now we have to take a glass slide. On this slide, with the help of the dropper, you are just going to put only one drop of the suspension on this slide. Okay, and this suspension is to be covered with the glass slide. Okay, once you cover this glass slide, then you will place it on the stage of the microscope, and you have to adjust it. Now you will have to observe the particles, and you will have to write down how many particles fall into which range. Okay, now we will see how you see the particles through the microscope. So this is the way in which you see the particles through the microscope. Okay, if you see the scale, okay, now using that scale you have to measure almost 300 to 500 of the particles, and you have to determine its particle size. So using this eyepiece we are going to measure the particle size for almost 300 to 500 of the particles. Okay, once this particle size is determined, then we will move forward to the calculations. Okay, so once the particles are calculated, now we will see the observation table and how do you write the result and conclusion.
Now we will see the observation table. Okay, so the observation table, it consists of the size range, mean size, okay, it is in micrometers, then number of the particles which you have counted, then percent particles, percent frequency. This is ND, it is number of particles into mean size range. Okay, it's square, it's cube, and raised to the power of 4. Okay, So now we had taken this range 0 to 5, 5 to 10, 10 to 15, 15 to 20, 25, 20 to 25, 25 to 30. Okay. The mean of 0 to 5 is 2.5. Mean of this size range is 7.5. Mean of this range is 12.5. Mean of this range is 17.5. Of this range is 22.5, and mean of 25 to 30 is 27.5. Okay. So, for this particular size range, we counted particles. We counted the number of 75 particles. Okay. Then again 75 particles were found to be of the size range 5 to 10. 60 particles in that particular area, they were in the range of 10 to 15. 50 particles, they were in the range of 15 to 20. 38 particles which were counted of the size range 20 to 25. 22 particles, they were of the size range in between 25 to 30. Okay. So now we have converted this number of particles into percentage. How? The total number of particles which we calculated, the total of all these numbers, it is 320. Okay. Now what you have to do, 75 particles out of 320, they were of size range 0 to 5. So how you are going to calculate the percentage? That means 75 divided by 320 into 100. Okay. So the percent of particles in the size range 0 to 5 was 23.43. For the particle size range 5 to 10, it was 23.43. For size range 10 to 15, it was 18.75. These values, these are based on this number of particles. Okay. Then for size range 15 to 20, the particles out of total particles, okay, out of 100 particles, 15.62 particles, they were in the size range of 15 to 20. So we can say from this calculations. Okay. Then out of this all 320 particles, 11.87% particles, it fell into the size range 20 to 25. Then 7.812% of the particles, they were in the size range of 25 to 30. Okay. So now next column, it is the percent frequency. What is done? You just have to go on adding the lower value. Okay. So first we have taken this 23.43. Okay. To this is added. So 23.43 gives you 46.86. To this 46.86, we are going to add 18.75. It gives you 65.61. To this value, we are going to add 15.62. It gives you 81.23. Plus 11.87, 93.1. Plus 7.82, 100.9. Okay. Then next column is ND. It is just multiplication of number of particles into mean size range. Okay. So this column, it consists of multiplication of these two columns. Okay. So the summation of this is 3835. Okay. Then you have square of this ND. Okay. You have to take this value and you have to square it up. Okay. So the values are written over here. Its total is taken over here. Then ND raised to 3. The values are written. This value is raised to 3. Okay. So this value is raised to 3. 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 And this the cube of all individual figures, it is determined. Okay. Then you have to sum it up. And then similarly you have to calculate the amount, okay, the number for raised to the power of 4, and then you have to take its sum. Okay. So this is very simplified calculations. Okay. So now we will see the calculation for arithmetic mean diameter. Okay. Arithmetic mean diameter, it is indicated by DIN, and it is calculated as summation of ND divided by summation of N. Okay. We have put those values. So we get arithmetic mean diameter to be 11.95. Then you can determine the surface length diameter. Okay. It is calculated by the formula summation of ND square divided by summation of ND. Okay. So by putting the values, you get surface length diameter to be 724.05. Okay, then you have volume surface mean diameter. So its formula is this. Okay, after putting the values, you get the diameter to be 764.51. Next is weight moment mean diameter. It is calculated by using this formula. Okay, by putting the values, you get that diameter to be 787.60. Then next thing which you can calculate is surface number mean diameter. The formula is this. By putting the values, you get the surface number mean diameter to be 93.15. And lastly, you are going to determine volume number diameter, whose formula is this. By putting the values, you get the volume number diameter to be 2575.63. Okay. Now we will plot a graph of mean particle size versus frequency. Okay. Over here we have taken mean particle size. Here we have plotted the frequency, and you get this type of curve. So in the result, we are going to tell the arithmetic mean diameter was found to be 11.98 micrometers. The surface length diameter was found to be 724.05 micrometers. Volume surface mean diameter was found to be 764.51 micrometers. Wet moment mean diameter was found to be 787.60 diameters. Surface number mean diameter was found to be 93.15 micrometers, and volume number diameter was found to be 2575.63 micrometers. Okay. So the most commonly asked question regarding this particular topic will be, you will be asked to define micromeritics. So you should know that micromeritics is the science and technology of small particles. Okay, micromeritics basically deals with the measurement of the size of very small particles. Okay. Then next question might be how the diameter is measured for non-spherical particles. This is very commonly asked questions, or you will be directly asked to define Martin's diameter, Faraday's diameter. Okay, anything can be asked, or you will also be asked to tell what is the projected area diameter. Okay, so these diameters, these are defined for non-spherical particles. Okay, so Martin's diameter is the averaged chord length of a particle which equally divides the projected area. The ferret's diameter is the average distance between pairs of parallel tangents to the projected outline of the particle, and projected area diameter is the diameter of a sphere having the same projected area as that of the particle. Okay. The next question might be, what are the methods to determine particle size? Okay, there are n number of methods. You just have to enlist few of them. So particle size determination methods, they for determining the particle size, you can go for optical microscopy, you can go for sieving method, then you can go for sedimentation method, or also you can go for conductivity method. Okay. Then the next question most commonly asked is, what are derived properties? Okay. So you just have to enlist the derived property. It consists of the density of the powder, which includes bulk density, tap density, granular density, true density. Then it also includes the flow properties of the powders, its porosity, bulkiness, okay, etc. The last question most commonly asked is, you have to explain the procedure of optical microscopy, because in this case calibration of the eyepiece is very important. Okay, sometimes only you'll be asked to write a note on calibration, or you'll be asked to explain calibration of eyepiece. Okay, so so the procedure of this is, the eyepiece of the microscope is fitted with the micrometer. Then the eyepiece micrometer is calibrated using a standard stage micrometer. The powder sample, it is dispersed in a suitable vehicle, or you can directly use a suspension or an emulsion. But you have to keep in mind that you are determining the particle size, so the particle, it should not get dissolved into that solvent. Okay, and its property, it should not get altered. Okay, then you will mount this sample on the slide, and you will place it under the objective of the microscope, and you will visually, you are randomly, you are going to visualize around 300 to 500 of the particles. Okay, and then you have to carry out the calculations, and you have to determine the diameter. Okay, so this was all about the experiment of optical microscopy. Thank you for watching.